Hey everybody, this is Larry. This is day 15 of the Leetcode Daily Challenge. There's going to be a weekly premium challenge later, so check that out. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's file. If I look like I'm in a mess, it is because I am a mess. Not gonna lie. Happy Friday, everybody, or Saturday. It is well, right now it's 75 degrees, but earlier it was in the 80s and 90s, which for the people speaking Celsius, was that like 30 degrees? Yeah, it's like high 20s and high 20s, say, right? I think I got a little sunburn. I'm eating a little bit of watermelon. My apologies. And on top of that is spring here in New York. So crazy allergies. Could not sleep last night, not gonna lie. No sleep. Hot. My air conditioner is messed up. I don't know what's going on with it. So Larry is miserable right now. Yeah, so just giving you some context. So if I'm a little bit slow, or if I'm like enjoying my watermelon a little bit too much, that is why. Alright, that's sorry, I'm swallowing it. Alright, that's let's take a look at today's problem. 2218, maximum value of K coins from piles. So you have n piles of coins on a table. Each pile consists of positive number of coins, which makes sense, of assorted denominations. In one move, you can choose any coin on top of any pile, remove it, and add it to your wallet. Given a list of piles, and piles of I is a list of integers denoting the composition of the I pile from top to bottom, and a positive integer k, return the maximum total value of coins you can have in your wallet if you choose exactly k coins optimally. Okay, I mean, I think this is one of those problems where you have to look at the constraints very carefully, and then figure out how naive you can get, or brute force you can get, right? Let me think about this. This is probably not super. So I'm going to walk you through my thought process. I don't remember this problem, just in case you're wondering, but my initial thought is that so what are the states, right? For dynamic programming, we're trying to figure out the states, which is just basically the input for which, or what they call overlapping subproblems, right? Subproblems that we're going to reuse. And here we have n piles for the. So another way to think about this, right, is that let's say you have piles, right? You try and distribute k choices into n piles, right? So it's almost like so what you have is a multinomial function, right? Kind of. And a multinomial, of course, is just like binomial, but with more. Because basically you have some like, yeah, and you could calculate the number of choices. Man, I am not operating at good capacity. I mean, it's 75 degrees outside. It's actually even warmer here inside. It's 82.5 degrees inside. The fan has not been working. Sorry if I'm complaining too much, but this is why, like, I don't mean to be rude. I mean, you may ask, why is Larry eating watermelon during a video? It's because this is the only way I can cool down. So I'm sorry, friends. Desperate times calls for desperate measures. Okay, but basically the way that as it happens with dynamic programming or even brute force in a way, is try to figure out is there a way to impose some sort of ordering or structure, right? Because the key part of dynamic programming is going to be this idea of overlapping subproblems, and the overlapping subproblems takes advantage of usually a structure that you can kind of that you can kind of repeat in some way, right? So okay, so and in this particular problem, what I mean by that is that you can go from left to right with no loss in generality, right? Or as they call it, or yeah, I think there's no loss. Without a loss in generality is what they call it in mathematical proofs. But basically, for example, if you want to put five, or I say put, but if you want to pick five things from power one, it doesn't matter what order you do it in, right? Like, so then you might as well just go from left to right. So here it gives us our first dimension. Let's just say calculate. I'm lazy to name things. You have index, which is the current index, and then maybe k left, right? Basically, k left is just what it sounds like. That how many things we still have to choose. Technically, there are two ways you can kind of write this, and it really depends on it really depends on what you value more. Sometimes, depending on the constraints, and what I mean by that is either a space, or you value space more, or you value time more. So the time will be the same, but the space allow you to use certain subproblems more efficiently. And what I mean by that is that for here, the naive thing to do would be just something like for x in range of k left, which plus one maybe. So that means that we want to take x items from top of the pile, right? So you can do that here, but you can also, in theory, so we do some magic here. I'm talking at a high level because this is a hard problem. If you struggle with dynamic programming, definitely work on the easier problem first, because this is not an easy one. Maybe it's not a super difficult one, but it's definitely not an easy one either. So definitely go, because I'm kind of choosing to spend this time going over kind of a, I wouldn't say advanced topic, but at least a topic that you get to play around with, and kind of try to teach a little bit in that direction, right? So that's what I'm going with today's video. So sorry, but yeah, but basically here you could do maybe something like calculate index plus one, k left minus x, or something like this, right? Plus getting the scores from piles, and then your best is equal to 0, your best is equal to max best. You have this plus return best, something like this, right? So there are a couple of things like getting the scores and whatever, and keeping track of x is less than number of powers and stuff, but this is the general structure of the code. We'll add some if statement later. So that's one way to write it, right? The other way to write it is kind of similar, but what I like to call it memorize or unrolling the loop. It's not really depending on who you ask, because basically for me it just feels like a technique that you used to use to optimize in say C, where they unroll loops to kind of manually do things. It's not quite that, but the way that I think about it is something like this, where now you have added an extra dimension here, right? So you have best is equal to 0, and then now what is it saying is the top of, I mean, p index is a terrible name, but it's basically saying, okay, how many have we taken from the top of the pile, right? So then you can maybe do something like, okay, so best is equal to max of either we don't take it, so that's calculate index plus 1, because we go to the next one, and then 0, and then k left, or we do take it, which is calculate of index, p index plus 1, k left minus 1, plus like piles of index of p index, or something like this, right? So I mean, I'm rushing this part a little bit, but basically I just want to write out the structure. And of course you would memorize both of these. That's why I call unrolling the loop, because in terms of time, this should be both the same-ish, depending on how you kind of want to figure it out. Because yeah, this will get calculated. It's just that as part of this, you can think about using just one item and then that gets cached. Which one makes more sense depends on the problem and the constraints and stuff like this. But I just want to kind of use this as an opportunity to show off a little bit of like things that you can do. And it's not always set in stone, and it really depends on, like I said, the constraints. Yeah. So let's take a look at the. Ooh, ouch. Yeah, take a look at the constraints. This is kind of expensive. I don't know if this is fast enough. Because basically here we want to say that, index is equal to 0 to n. K left obviously is going to be 0 to k, right? So this is n O of n times k plus or times another k, right? So this is going to be n times k times k. So that's going to be too slow, right? In this case, index is also 0 to n. P index is maybe like, I don't know how you want to say it, but the summation of all the P indexes will be k, right? Or less than k, but less than 2000 anyway, whatever this is. Sum of P, say, right? 0 to some P, I don't know. K left is going to be just 0 to k. So this is also comparable. So I don't know. This is, and obviously if you kind of think about it, both of these, they would both be too slow. And then the idea now is try to figure out, is there a way to optimize? People ask me to click on this, I guess. This is a good time for me to use some watermelon. I'm trying to think. The analysis of this is very naive. Powers doesn't matter. 0 to k makes sense. I think there's a there's a bit of relationship that goes here with respect to how many gets used. Because basically, okay, maybe I'll play around with this for a second, right? Basically, there is some amortization thing, but maybe the math is a little bit too difficult for me. So the way that I would maybe think about it is, okay, what happens if you have, say, 2 piles of 1,000 each, right? So you have 2 piles. K is equal to whatever 2,000, right? And then you have 1,000 on the. So then that means that, so that's, you have something like this, 1,000 items, right? That you have to loop through. So then here, the complexity is going to be O of 2 times 2 million times 1,000, right? So that's okay. But what if you have n is equal to 1,000, k is equal to 2,000 because that's the easiest max case, and then now you have, I don't know, let's just say 1 dot dot dot, and then I don't know, what is it? I don't know, 1,001 left, right, or something like this. in this case, you have n, right? And then here, there's all these have no decision. It's all ones. And then here is 1,000. So you actually only have 1,000 times 1,000, effectively, right? I don't know. This is a very tough mathematical analysis. I think this is fast enough. And during the contest, I wonder if I YOLO, to be honest. Let's take a look. All right, let's actually solve it this way then, and then see, right? All right. So yeah, items is equal to, or maybe just call L is equal to length of pile sub index, and then this or min of this, and k left, right? I'm trying to think whether it's +1 here or over there. I don't remember. +1. Okay, and then that's it, right? And score is equal to 0. We add it to piles sub x, or sub index of x, and that's it. The only thing that we haven't done is that we want to do the skip one, so this skips it. And then also if index is equal to n, we return, I guess we return 0. I mean, even if you have k left, even though that's a very awkward bit, right? Something like that. All right, this may I'm just trying to see for correctness. I know that I didn't do the caching yet, but why do I get a 116? Did I have it off by 1 or something? Oh, yeah. Maybe I could have written it. This is very awkward actually, but maybe I could have written it this way. And then I don't need this. Alright, gotta wait for this one. This one wrong. I'll put 6, but 706. I guess this needs to be +1 then. Yeah, and then this, it's a little bit awkward actually. I don't know why I wrote it this way. Maybe I should have done it the other way. Oh well. Okay, so this looks good. Of course, we have to memorize. You should, and I will keep doing it this time. So has cache is equal to force, times k or k +1. K +1 for and n, right? And then cache, we can just do the same thing, right? And then maybe we can do something like if. Something like that. It looks fast enough. Let's give it a spin. Why not? We'll see. Eat some watermelon. Surprised that worked. So during the contest, and that was a year ago, huh? Cache uses too much memory. You cache uses time limit. And then I What the? I see what I did here. That's actually clever. Actually, I like the way that I did this during the contest, I guess. I'll actually go with this solution as well. Give me a second. Let me take a look. Yeah, I did it again afterwards. Okay. Well, there's no way to prove that this is fast enough. Maybe I'm wrong. But yeah, but this is. So the way that I like the way that I did the other one. So this one I'm not going to explain anymore. This is just pretty brute forcey, and actually I have no good way of proving it. I was hoping that past Larry have it, but I actually like this solution a little bit. Basically, what I did was I unrolled the pile. So let me actually. That's actually pretty cool, huh? Actually, past Larry, props. Current Larry, you're trying your best. I appreciate you, but all right. I'm just putting my drawing. So basically, the idea behind the one that I did during the contest, which I like a lot, actually. Even though I imagine I'm probably pissed that the naive solution worked. I don't know. These things are hard to kind of figure out. But basically, the idea is that okay, let's say you have a lot of piles. Let's just say 1, 2, 3, right? I don't know, 4, 5, something like that, right? So basically, the way that the new code is doing is kind of very similar to what I said earlier about unrolling the loop. In that basically now, I just basically put it into one giant array, if you will, of 1, 2, 3. Oops, I don't know how they came out that way. Pretend they're 1, 2, 3, 4, 5, 6, 7, 8, 9. Or I think I wrote them the other way. So pretend because I think you're supposed to have it from the top first, but I wrote it from the bottom first. Whatever, you get the point, right? So basically, what I did is that I rearranged the things so that it looks like this, and then basically for every index, I have two choices. I can either skip this and go to the next item. Right, makes sense. This is normal dynamic programming things. You either use or you don't. So you can either use and then go to the next item, or you can use and go to the next next pile, right? By skipping ahead, almost like just like skipping ahead. And you only really have 3 choices now, right? You have either not buy or not pick and then go to the next index, or pick and then go to the far index. And even then, I don't even know that you have to. Oh wait, you have to, because otherwise, because you don't want to accidentally pick 3 by accident if you just keep going. That's right. That makes sense. And the reason why I like this one a little bit more than the way that I did it today is because if you look at this code, is what we have. Is basically the reason is because now you look at this. What is index, right? Index is 0 to 2,000 because, as they said, there are most 2,000 items. What is k? Well, 0 to k. Also, so now you have 2,000 square instead. So now you could prove that it is only 4 million things, right? 2,000 squares, 4 million, and each of them does a constant amount of work, so that's going to be good enough. So that's basically the reason why I, looking at this one, I like it a little bit more. But yeah, that's all I have for this problem. That's all I have for today. Let me know what you think, and yeah, stay cool. I'm trying my best to. So yeah, stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.